Hello students, welcome to Educate. We are going to continue with the chapter number 5 of class 12 physics. So in previous lecture we have studied about its basics. Now we are going to continue with the examples and some other concepts. So let's start. Example number 5.2. Here figure is given. We have to find out the stable and unstable equilibrium. So let's see what the question says, and after that we are going to analyze. Figure 5.4, this figure shows a small magnetized needle P. This is a needle P placed at a point O. The arrow shows the direction of the magnetic moment. The other arrows show different positions and orientation of the magnetic moment of another identical magnetized needle Q. Right? Now, in which configuration the system is not in equilibrium? So, what does this mean? Equilibrium means what? Equilibrium means the two arrows should be parallel, right? The basic concept means if you analyze the situations, you can say this is direction of magnetic field and magnetic dipole is also placed like this. So, theta is equal to 0 degree, right? If it is 180 degree, then it will be unstable. In case theta is 90 degree, in that case you will say that total value is 0. So here we can analyze the situation. Parallel to P, which point? This is parallel to P. This point is parallel to P. What about this? This is anti-parallel. This is anti-parallel. And in these cases, this and this perpendicular here in this direction Q2 is perpendicular. So these two cases are perpendicular. These two are, this one and this one are anti-parallel. This one is parallel. This one is parallel. So I think you have understood. Stable means parallel and unstable means not parallel, and in case of perpendicular it will be 90 degree. So we can read the answer also, but the same thing they are going to tell here. Potential energy of the configuration arises due to the potential energy of the one dipole, say Q, in the magnetic field due to the another. Use the result BP, you know, this is on the normal bisector. BP is given mu naught 4 pi r cube MP. I think you remember when we find magnetic field due to a dipole on its, this is perpendicular bisector, it means this is equatorial and this is axial, right? So here the only one thing we will observe, that what is the direction of this. This is like MP. So stability, as I told you, when the two arrows will be in same direction, the same thing they have written here. We can go to next page and we can see here they are saying, for instance, for the configuration Q3, for which Q is along the perpendicular bisector dipole P, the magnetic moment of Q is parallel to the magnetic field at the position 3, hence Q3 is stable. So those positions in which the two are parallel, that will be stable. PQ1, PQ2, these are the cases of perpendicular. PQ3, PQ6 are stable, parallel. PQ5, PQ6 are anti-parallel, right? So these things you have understood. Now we are going to see what is Gauss law in magnetism. What does it say? So Gauss law in electrostatics, you know very well. Here in magnetism, if we compare the Gauss law, what do we find? In case of electrostatic, what is Gauss law? Integration E dot ds. E dot ds. What does it give? Q upon epsilon naught. Correct? In case of magnetism, it means it gives net flux, right? This is equal to phi E. Means it is not necessary that incoming flux and outgoing flux are equal. But in case of magnetism, incoming and outgoing flux must be equal, because if you consider this, so suppose this is north pole, this is south pole, one line comes like this, so it must enter. So if you take it a positive, then it must be negative, right? the sum will be 0 in every case. So here integration b dot dl, if we try to find out, so it will be 0. And this justifies that there is no monopole, right? For detail, you can read the passage, you will understand. Here, many of the diagrams given in the figure show magnetic field lines, thick lines in the figure, right? Show magnetic field lines, point out the wrong one. Some of them may be described electrostatic field lines correctly, point out which ones, right? So here, is it correct to say that this is the North Pole and then all field lines are coming out? So that is, that is not possible. Here, where is South Pole? That will be the question, because they form closed loops. So this is a wrong one. If you observe the answer, it's written here that field lines can never emanate from a point as shown in the figure. Over any closed surface, the net flux B must always be 0. So pictorially, as many field lines should seem to enter the surface as number of lines leaving it, the field lines shown in fact represent the electric field of a long positively charged wire. That is possible because all field lines are coming out. The correct magnetic field lines are circling the straight conductor. So that we have already studied. Now we are going to second point. In this case, what is happening? There is empty space, these lines are intersecting, and you know that be it electric field lines, be it magnetic field lines, they never intersect. Then comes, suppose we go this, we see this is toroid. All field lines are inside only. Of course, in case of toroid, field lines remain confined within the toroid. So we can see the answer also here. Magnetic field lines, like electric field lines, can never cross each other because otherwise the direction of the field at point of intersection will be ambiguous. There is further error in the figure. Magnetic field lines can never form closed loops. There is closed loop also in the diagram if you observe. So that is wrong. Here in this case, magnetic lines are completely confined within a toroid. That is correct. Nothing wrong here, you understand. Then comes field lines due to solenoid. Let's see the picture once again. So this case, they are confined, correct, and they are parallel. This is D part. So here, what is wrong then? Field lines due to solenoid at its ends and outside cannot be so completely straight and confined. So there is one concept. At the end of the solenoid, field suddenly reduces to half and then its value becomes almost 0, right? But in the picture, what do you observe? You observe that field lines are continuously straight, means field is uniform. It's non-changing. So that is not possible in any case. Then comes here. Is it closed curve? Is it correct? So of course it is correct. These are field lines outside inside a bar magnet. That is simple. Then comes next one. Next one says here E part. What is happening? Right here, these shapes are shown. This type is happening. So this is also not correct. These field lines cannot possibly represent a magnetic field. Look at the upper region. All the field lines seem to emanate out of the studded plate. That is so the net flux through a surface surrounding the shaped plate is not 0. This is impossible for a magnetic field line. So you can read it. It is simple. And then last point is, in last diagram, what do you observe? What is happening? Here NS is shown and here the field lines are shown. If you observe it carefully, here these are the field lines, right? And then what is happening? What is wrong here? So magnetic field lines between two pole pieces cannot be precisely straight at the ends. Some fringing of the line is inevitable. otherwise ampere's law is violated. This is also true for electric field lines. So here the field lines are shown completely straight, and that is not possible. Now let's go to next questions. Here question number 5.4 says magnetic field lines show the direction at every point along which a small magnetized needle aligns at the point. Do the magnetic field lines also represent the lines of force on a moving charged particle at every point? So this point is explained in the note that this is not the case. The magnetic force is always normal to B. Remember, magnetic force F equal to QVB. It is misleading to call magnetic field lines as lines of force. This is important. You have to keep in mind for exam purpose, right? Then comes Gauss law in magnetism. We have just studied that Gauss law in magnetism states that B dot dl becomes 0. So the same thing is asked here. If magnetic monopoles existed, how would the Gauss law of magnetism be modified? So this is good question. So if there will be net charge, sorry, here net magnetic strength like V dot d is equal to 0, but if it is not 0, in that case what would happen? So there will have to be Qm as a result. So here let's read it. Gauss law of magnetism states that flux of B through any closed surface is always 0. B dot ds equal to 0, that we know. If there is monopole, so this 0 will not be there. There will be pole strength instead. So if monopoles exist, the right hand side would be equal to the monopole enclosed by S. Correct? Analogous to the Gauss law of electrostatics. So that could be the correct answer. And then next point says that does a bar magnet exert a torque on itself due to its own field? Does one element of current carrying wire exert a force on another element of the same wire? So answer to this point is no. There is no force or torque on an element due to the field produced by that element itself, but there is a force or torque of an element of the same wire. For the special case of straight wire, this force is 0. And the last question is magnetic field arises due to charges in motion. Can a system have magnetic moments even though its net charge is 0? So answer is of course yes. The average of the charge in the system may be 0, yet the mean of the magnetic moments due to the various current loops may not be 0. We will come across such examples in connection with paramagnetic materials where atoms have net dipole moment though their net charge is 0. So this point we will study later. Now there are certain properties of a magnet like magnetization, magnetic intensity, etc. So the first point related to this concept is magnetization M. So it is equal to magnetic moment divided by volume, right? So M is a vector with the dimensions L minus 1A and it is measured in unit of ampere per meter. Now we can consider a long solenoid of n turns per unit length and carrying current I. The magnetic field in the interior of the solenoid, as we have already found, that B0 equal to mu naught Ni. If the interior of the solenoid is filled with a material with a non-zero magnetization, the field inside the solenoid will be greater than B0 because there will be addition of a field. The net B field in the interior of the solenoid may be expressed as B0, this value, plus due to this magnetization Bm, and we can find the expression for it. Bm equal to mu naught M. So Bm is proportional to the magnetization M. So we can get the result, right? Now it is convenient to introduce another vector field H called the magnetic intensity. So this is given H equal to B naught B upon mu naught minus M. Here H has the same dimension as M and is measured in units of ampere per meter. Thus, the total magnetic field B is written as B equal to mu naught H plus M, right? Because from here we can put the value of M at this place, right? And then we can evaluate. Now we repeat our defining procedure. We have partitioned the conditions to the total magnetic field inside the sample into two parts. It's a relation we have previously also mentioned, so you have to keep in mind. Now, here we define the other is due to the specific nature of the magnetic material, namely M. The latter quantity can be influenced by external factors. So here we can define M is chi times H. Alright, we know M, we know H, where chi is dimensionless quantity and is appropriately called the magnetic susceptibility. So now we are going to relate magnetic susceptibility with B and H. So final relation that we get B equal to mu naught 1 plus chi times H, and this is also equal to mu naught mu r and H, which these two can be written as mu, so mu H. This relation is very important, mu r equal to 1 plus chi, right? And then we define this mu equal to, here we have made assumption mu equal to mu naught r, or mu naught times r is 1 plus chi, this value mu naught, and then there will be a relation, and on the basis of these values we will categorize the different type of materials in next section. Before that, we are going to see this numerical. The numerical says there is a solenoid which has core of material with a relative permeability 400. Mu r is given 400. The winding of the solenoid are insulated from the core and carry a current of 2 ampere. We are given the value of current. If number of turns are 1000 per meter, so that is value of small n. We have to find out H, M, B and magnetizing current Im. So question is simple. We can easily calculate. So let's do it one by one. The field H is dependent of the material of the core and given by H equal to Ni. So in our question, I is given 2 ampere, number of turns is 1000, so we get 2 into 10 power 3 ampere per meter. Then comes magnetic field B. So this we have already studied that B equal to mu r times mu naught times H. Mu r relative permittivity is given 400 and mu naught, you know, 4 pi into 10 power minus 7, and value of H you have already evaluated from here, so you put that value here. So you will get B equal to 1 Tesla. Then comes magnetization. We write formula B equal to B minus mu naught H whole divided by mu naught, and we further simplify. So we will get this as mu r minus 1 times H, and then we can put the value of H from here, and this comes because mu r is 400 minus 1 is 399 times H, we will get this. And last part is the magnetizing current Im is the additional current that needs to be passed through the winding of the solenoid in the absence of the core, which would give a value B as in the presence of core, right? So we can write B equal to mu r n times I plus Im, and we are given the values. B is 1 Tesla, we have evaluated here, and current is given 2 ampere, and other factors are also given. Relative permittivity is given as 400, so we can put those values. Number of turns is given 1000. So after putting those values, we get Im equal to 794 ampere. I think you have understood. Now we are going to see some magnetic properties of materials. So here we will see diamagnetic, this is diamagnetic, paramagnetic, ferromagnetic. So diamagnetic, it opposes the magnetism, right? Paramagnetic means it has magnetism up to certain extent. Ferromagnetic means highly magnetic material. So we compare these values, chi, mu r. So here for diamagnetic material, chi lies between -1 and 0. Suppose you are given value of chi as 0.2, then you will say that this is what? Diamagnetic. It can be negative also, right? Sorry. it must be negative, but it should not be beyond -1. Suppose you are given plus 0.2, it means it will be a paramagnetic, right? If it is 200, in that case it will go to ferromagnetic, correct? If it is say minus 0.5, in that case it will be a diamagnetic. It means susceptibility is negative for diamagnetic. For paramagnetic it is positive, and for ferromagnetic it is also positive, but its value is stronger. Then comes mu r. Mu r lies between 0 and 1. Here mu r lies between 1 and 1 plus sigma. And here mu r is greater than 1. Then comes mu is less than mu 0. In this case, mu must be greater than mu 0. And here, very large value. Here, the magnetic field lines are also shown that if it is diamagnetic, then what is happening? Field lines are pulled, means pushed away from the material. In this case, field lines are going inside, paramagnetic. So next point is, here the same thing that we have compared, it is given. Here one important point we will discover. The most exotic diamagnetic materials are superconductors. These are metals cooled to very low temperature, which exhibits both perfect conductivity, means there is no resistance, and perfect diamagnetism. Here the field lines are completely expelled. There is no field line inside. X equal to -1, perfect value, mu r equal to 0. A superconductor repels a magnet, and by Newton's third law is repelled by the magnet. The phenomena of perfect diamagnetism is superconductors is called the Meissner effect, that you will study in higher classes after the name of its discoverer. Superconducting materials can be gainfully exploited in a variety of situations, for example, for running magnetically leviated superfast trains, etc. So you can study about these materials later on, and they are some interesting materials. Their properties are quite good. So now we are going to see paramagnetism. Paramagnetism means they will show, such materials will show certain magnetic effect, right? But they are weakly attracted by the magnets. Paramagnetic substances are those which get weakly magnetized when placed in an external magnetic field. They have tendency to move from a region of weak magnetic field to a strong magnetic field. They get weakly attracted to a magnet. The individual atoms like ions or molecules of paramagnetic materials possesses a permanent dipole magnetic moment of their own. Keep in mind, on account of the ceaseless random thermal motion of the atoms, do not no net magnetization is seen, means net effect will get cancelled in the presence of an external field B0, which is strong enough, and at low temperature the individual atomic dipole moment can be made to align and point in the same direction as the applied field, right? So here some more properties are there, that bar magnetic material placed in an external field, the field lines gets concentrated inside the material and the field inside is enhanced. In most cases, this enhancement is slight, being 1 part of 10 power 5 when placed in non-uniform magnetic field. Some paramagnetic materials are aluminum, sodium, calcium, oxygen at STP, standard temperature and pressure, and copper chloride. For paramagnetic material, both chi and mu r depend not only on the material but also on the sample temperature, right? So you can study about these properties later on. Now, next point is ferromagnetic materials. Here magnetic domains are shown. When field is applied, then they all get aligned. So here the individual atoms or molecules in a ferromagnetic material possesses dipole moment as in paramagnetic material. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a microscopic volume called domain. So small domains are there in which these all are aligned, right? The explanation of this cooperative effect requires quantum mechanics and is beyond the scope of this. So we are not going to discuss about that. When they are placed in external magnetic field, then all domains are aligned, and hence they will behave like a giant magnet, or they will behave like a complete magnet. So you have understood. Thus, in a ferromagnetic material, the field lines are highly concentrated in non-uniform magnetic field, the sample tends to move toward the region of high field. We may wonder as to what happens when the external field is removed. So if external field will be removed, then what will happen? These domains will arrange themselves as they were earlier. We may, in some ferromagnetic materials, the magnetization persists, right? So these domains may remain aligned, but in some cases they will again get disturbed. Such materials are called hard magnetic materials. Hard magnetic materials means when they are placed in magnetic field, they all align themselves, and this alignment persists for longer period, right? Alnico, an alloy of iron, aluminum, nickel, cobalt, and copper is one such material. The naturally occurring lodestone is another. Such materials form permanent magnets to be used among other things as compass needle. On the other hand, there is a class of ferromagnetic material in which the magnetization disappears on removal of the external field, as we have discussed. Soft iron is one such example. Appropriately enough, such materials are called soft ferromagnetic materials. So you have seen two types of ferromagnetic materials. Hard magnetic materials. Hard magnetic materials means what? When they are placed in magnetic field, all domains get aligned, right? But when magnetic field is removed, still they remain aligned. But in this case, in case of soft ferromagnetic materials, these domains will remain aligned as long as there is magnetic field. But when magnetic field is removed, then what will happen? They will again get disturbed, means their alignment will cancel, right? So there are a large number of elements which are ferromagnetic: iron, cobalt, nickel, gadolinium. The relative magnetic permeability is more than 1000. So the ferromagnetic property depends on temperature also. At high temperature, a ferromagnetic becomes a paramagnet. The domain structures disintegrate with temperature. This disappearance of magnetism with temperature is gradual, right? So this is all about the chapter. I think you have enjoyed. So we can read the summary and then we will give an end to this lesson. The science of magnetism is old. It has known since ancient times that magnetic materials tend to point in the north-south direction, like magnetic magnetic poles repel and unlike attract, and cutting a bar magnet in two leads to the smaller magnets. And magnetic poles cannot be isolated, as you know. If you keep on cutting, still you will get a magnet with two poles. When a bar magnet of dipole moment M is placed in uniform magnetic field, then the force in it is zero. There will be torque M cross B, and its potential energy will be minus M dot B, where we choose the zero of the energy at the orientation when M is perpendicular to B. Means dipole is perpendicular to this. Means magnetic field is in this direction and orientation is this direction. So angle between the two is 90 degree. Correct. Consider a bar magnet of size L and magnetic moment M at a distance R from its midpoint. When R is greater than L, then magnetic field along axial point, you know, B equal to mu naught M divided by 2 pi R cube, and along equator it will be just half and direction will be just opposite. Then we come across Gauss law that gives B dot ds equal to 0, means no monopole exists in case of magnetism, unlike the electric field. There can be positive and negative charges separately, they separately exist. But in case of magnet, if we say that north pole is there, south pole is there, and they separately exist, so that is not possible, and that is justified by Gauss law of magnetism. Correct. Then comes consider a material placed in external magnetic field B0. The magnetic intensity is defined by B0 divided by mu naught. Then magnetization M of material is defined by M divided by, here we divide by magnetic moment per unit of volume, right? M of the material is its dipole moment per unit volume. So dipole moment divided by volume will give M. The magnetic field B in the material is given by mu naught H plus M. For a linear material, M equal to chi times H, so that B equal to mu H, and chi is called the magnetic susceptibility of the material. The three quantities, chi, the relative magnetic permeability, that is mu R, and the magnetic permeability mu, are related by the formula, like mu equal to mu naught mu R equal to 1 plus chi, And then comes last point. Magnetic materials are broadly classified as diamagnetic, paramagnetic, ferromagnetic. For diamagnetic material, chi is negative, and small, and for paramagnetic material, it is positive, and small. Ferromagnetic materials have large chi and are characterized by nonlinear relation between B and H. And finally, this is linear relation, or this is linear relation. Now, substance which at room temperature retain their ferromagnetic property for a long period of time are called permanent magnets. So, this is how chapter ends. Here some points are there which you can read. This will be helpful, and here there are some numericals. We will study these numericals in next lecture. Thank you for watching. Team Educate.